everyone. This video lecture is on valence bond theory and molecular orbital theory. So before you dive into either one of these topics, please go back and make sure to review your general chemistry 1 topics on Lewis structures, how to form Lewis structures, how to determine resonance structures, formal charges, expanded octets, polarity, and molecular geometries and electron geometries. And it may help to go back and review your quantum mechanics section as well, especially your s, p, d, and f orbitals. So this is just an image of your different molecular shapes. Remember, these are your number of electron regions and the electron geometries that are associated with each. So that's the most important section. Remembering your linear, your trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. And keep in mind that those X's that you see around the central atom, those could represent lone pairs, or they could represent atoms, right? So for example, with an electron with 3 electron regions with a trigonal planar structure, one of those could be lone pairs and 2 of them outer atoms. Okay, so just go back and review those sections. Now, the problem with the Lewis model is that it can generally predict trends and properties, but it doesn't give us good numerical predictions for our bond strengths or our bond lengths. It's also not great at predicting the actual angle in your molecules. And we've seen with resonance structures that you have to, if you have a resonance structure, you may have 2 or 3 or more resonance structures that you need to form in order to give an accurate picture of that molecule. Okay, so there's not just one correct structure when we have resonance. And then it's also not great at predicting magnetic behavior. So later on, we'll look at paramagnetic and diamagnetic molecules. So there are limitations to the Lewis models that we looked at in General Chemistry 1. So in this topic, we're going to look at 2 advanced bonding theories. We're going to spend most of our time focused on the valence bond theory and then a little bit of time touching on molecular orbital theory. So the quick differences between these two is that valence bond theory, that's going to focus on localized electrons on particular atoms. So we're going to take our atomic orbitals that we learned from Gen Chem 1, our s, p, d, and f orbitals, and we're going to hybridize those. Okay, with molecular orbital theory, the electrons are going to be delocalized, and so we're going to form what we call molecular orbitals. Okay, so those are some quick differences between the two. So now we're going to focus on valence bond theory. So valence bond theory is a quantum mechanical model that just shows how electron pairs are shared in covalent bonds. And so we're going to see overlap between atomic orbitals, and that overlap is going to represent the covalent bonds. Okay, so here's some quick images from General Chemistry 1. Remember, your s orbital is a sphere, right? And we just have one s orbital per shell. Okay, your p orbitals, remember that we had 3 of those. You could have one along the x-axis, and that's your px orbital. You could also have a p orbital along the y-axis or along the z-axis for a total of 3 p orbitals per shell. You have 5 d orbitals, and you have, 5 d orbitals and 7 f orbitals per shell. And just as a quick refresher too, when you look at a periodic table, remember that we can block off our s, p, d, and f, right? So the first 2 columns of your periodic table represent your s orbitals, and remember that there are 2 electrons per orbital. So those 2 columns represent 1 s orbital per shell. So in the first shell, we have a 1s orbital. In the second shell, we have a 2s orbital, right? And those tend to be represented by a single horizontal line, and we can have an electron spin up and an electron spin down in a single s orbital. And then for the p orbitals, remember there are 3 of those, right? And we can have up to 6 electrons, 2 per p orbital. And of course, we would feel them all spin up and then go back and do 3 more. And right, so that would be 3 p orbitals in a single shell. And so like we have our 2 p orbitals in our shell 2, or our principal quantum number equals 2. And again, 3 p orbitals that are in the 3p shell. Now for the d orbitals, you have 5, right? 5 d orbitals per row or per shell. And so again, if you were to have 2 electrons in each d orbital, that gives you a total of 10. And so that kind of explains the periodic table, why we have 2 columns in the S block, 6 columns in the P block, 10 columns in the D block, and then remember your F block are your lanthanide and actinide series that fall underneath your periodic table, right? This is the F block here. And you would find that those are 14 columns, right, for a total of 7 orbitals, 2 electrons per orbital. So that's just a quick refresher of Gen Chem 1 and your sp and d and f orbitals. So in valence bond theory, the first thing we're going to talk about are sigma bonds. So sigma bonds are whenever you have an overlap between 2 orbitals and they have to be directly at each other, pointed directly at each other. Okay, so this can happen between 2 s orbitals. So here we've got 2 hydrogen atoms, right? In the very center is our nucleus. Okay, and in the center of each one of those, we would have a hydrogen atom surrounded by 1 s orbital. And then that overlap here in the center, right? And maybe I should change my color. But this overlap right here in the center, that's where that sigma bond is occurring between those 2 hydrogen nuclei. And then we have 2 p orbitals that you can see below, right? And again, at the center, we have our nuclei, and you would have 2 f atoms, and these are the p orbitals. And so you would have 1 unpaired electron for each fluorine in that 2p. Right, and so you would be able to have those 2 electrons come together, and again, right here in the center, and I will change my color back to blue, right here in the center, again, would be that sigma bond. Okay, and then of course you could have it between an s and a p orbital, right? So a hydrogen atom would have an unpaired s electron, a chlorine atom would have an unpaired p electron, and again, you could have those come together directly at each other to form a sigma bond between. So the issue is that if we use those orbitals that we learned from Gen Chem 1, it doesn't always predict the correct number of bonds or the orientation of those bonds. And so we have to create what we call hybridized orbitals between these atomic orbitals. Now, when you're creating your hybridized orbitals, the total number of hybridized orbitals must equal the original number of atomic orbitals that you started with. So let's look at an example. So we're going to look at carbon. Okay, and carbon, we know, typically likes to have 4 bonds. And one of the best representations of this is methane, where we have a carbon attached to 4 hydrogens. Okay, so carbon likes to have 4 single bonds in a methane molecule. But if we look at the atomic orbitals and we lay it out for carbon with its electrons, we see that we've only got 2 unpaired electrons. So that would indicate that we would only want to have 2 bonds, but carbon likes to have 4. So what we can do is we can hybridize all of the valence orbitals that we have. And in order to determine the number of valence orbitals, remember those are going to have the highest principal quantum number. Okay, and the principal quantum number is listed right before each type of atomic orbital, right? So the 1s2, the 1 indicates your principal quantum number. So our highest principal quantum number in this example of carbon is going to be 2. And so the 2s2 and the 2p2, all of those represent your valence orbitals. And the superscript, those superscript 2's tell you the number of electrons in each type of orbital. So we have a total of 4 valence electrons in carbon. Okay, and so what we're going to do is we're going to hybridize the 2s orbital along with all 3 of the 2p orbitals. And when we do that, in this next example here, you can see that if we take all 3 of those 2p orbitals as well as that 2s orbital, and we create hybridized orbitals that all have the same energy level, we can take those 4 electrons and space them out so that we have 4 unpaired electrons. And so these new hybridized orbitals we call an sp3 because it came from 1 s orbital and 3 p orbitals. And to look at a picture of what this looks like, right, we have our s orbital here, we have our px, our py, and our pz orbitals, and we're going to create 4 new sp3 orbitals. Okay, and you can see one here along the z-axis. And when we put all 4 of those together, we get our tetrahedral structure that we remember from VSEPR theory in Gen Chem 1. Okay, and remember a tetrahedral structure, that's when you have 4 electron clouds around your central atom, and each one of those could either represent a lone pair or they could represent an atom. Okay, and so going back to those carbons that would be singly bonded to hydrogens, let's imagine that we have 2 carbon atoms. Okay, so right here in the center would be a carbon atom, and then the center here would be another carbon atom. Okay, and we're looking at C2H6, which is an ethane molecule. And so just to refresh what that would look like, you would have 2 carbons singly bonded between them, and each carbon would have 3 hydrogens. Okay, and so each one of those hydrogens are going to carry that 1s orbital, which is represented by each one of the blue balls in the picture, and then the carbons would each have 4 sp3 hybridized orbitals. And so right in the center, you're going to have a sigma bond between the 2 carbons, right between those 2 sp3 orbitals, and then you're going to have sigma bonds between each carbon and hydrogen overlapping from the 1s from the hydrogen as well as the sp3 orbital from the carbon. Okay. So we've looked at sp3 hybridization. We're going to take a moment to just review the other types of hybridizations that we can have. Keep in mind that the top 2 here, the sp3d2 and the sp3d, those come from our expanded octets. Okay, so remember those are going to be in row 3 or greater, so you're talking about something like phosphorus or sulfur. But things like carbon, nitrogen, oxygen, those cannot have expanded octets, and so those are not going to be able to dip into the d orbitals. And remember the reason why it's in row 3 or greater, if we go back real quick to our periodic table, remember that your d orbitals right here, they don't start until n equals 3, until your principal quantum number equals 3. Right, and that doesn't always match the row number, at least for your D and for your F block. Those are different. All right. So next we're going to look at sp2 hybridization. So this happens when you combine an s orbital with only 2 of your p orbitals. And so together you get a total of 3 sp2 hybridized orbitals, and you get 1 unhybridized p orbital at the top. Okay, so that energy level is not going to change, but the remaining 3 will have the same energy level. Okay. So when that happens, we're going to have 1 s orbital mixed with 2 p orbitals, and you'll get those 3 sp2 orbitals, and so that's going to give you your trigonal planar structure, right? Again, from Vesper theory, that's when you have 3 electron clouds. Okay, so when we hybridize only 2 of the p orbitals, that leaves that 1 unhybridized p orbital, and that is open to form what we call pi bonds. So pi bonds are going to be in a sideways fashion, right? And so if we look real quick ahead, remember a sigma bond is when they are going directly, kind of a head-on collision between 2 orbitals. But a pi bond is going to be when they are parallel to each other, which we can see here, right, between these 2 p orbitals. So they're kind of a sideways fashion for those pi bonds. So keep in mind that when orbitals are parallel to each other, you're not going to have as much overlap. And so sigma bonds are going to be stronger than pi bonds. Okay. And again, just going back to this picture, so this is where we've got more detail. We've got sigma bonds that are occurring between the sp2 hybridized orbitals, and then we've got 1 pi bond that's occurring between the unhybridized p orbitals. Okay, so if we were to count up the total number of sigma bonds, right, we have 1, 2, 3, 4, and 5 that are shown here, and we've got 1 pi bond, and this is for an ethene molecule. So remember, an ethene is going to be, let's give a little bit more space. That's where you've got 2 carbon atoms that have a double bond, and then you would have 4 hydrogen atoms, 2 coming off of each carbon. Okay, so your sigma bonds are going to be all of the single bonds between the carbons and the hydrogens, and it's also going to be the first bond between the 2 carbons. And then the second bond that gives you that double bond between the carbons, that's going to be your pi bond. Okay? So just keep in mind, this is especially important in organic chemistry, that when you have that sigma bond, you can have rotation between the atoms. Okay, so the orbitals can rotate around a sigma bond. But when you get a pi bond, that's going to lock in those orbitals. Okay, and you can't have that rotation anymore without breaking the interaction between the orbitals. And that's because if you look right here at the sigma bond, right, these orbitals, you could basically rotate them 360 and you're not going to break that interaction. But if you tried to rotate around the 2 atoms here in these pi bonds and you tried to rotate in this direction, right, then you would break that pi bond, okay? And so pi bonds, when you have those double and triple bonds, you're not going to have rotation between the nuclei. Okay. The next type of hybridization that we have is an sp hybridization. So that's going to happen if we take only 1 of the p orbitals and hybridize it with that s. And so we get 2 sp orbitals. And then we would have 2 unhybridized p orbitals that would remain with the same energy. And so when that occurs, again, here's your sp hybridization in a picture form, and that's going to give you 2 electron clouds, which would be your linear structure from Vesper theory of Gen Chem 1. And when this happens, when you have 2 unhybridized p orbitals, then you can have a total of 2 pi bonds between those 2 unhybridized p orbitals. And then, of course, you can still have that one sigma bond. And so the example that we have here most likely would be ethyne. So that's when you have a carbon that is triple bonded with another carbon and a hydrogen on either side. And so again, sigma bonds are going to be between the carbon and hydrogens. And then the first bond between the two carbons, that is also a sigma bond. And then the last two that form your double and your triple bond, those are going to be your two pi bonds. So in this image, we would have a total of 3 sigma bonds and 2 pi bonds in between the carbons. Okay, and then just real quick, for your expanded octets, that's when we're talking about those trigonal, bipyramidal, and octahedral electron geometries. So those are only going to happen when you can access the d orbitals for hybridization. So of course, n must be larger or equal to 3. So you're talking about atoms that are in row 3 or greater on your periodic table. And as you can see, for an sp3d, you would end up having 5 sp3d orbitals, right? 1, 2, 3, 4, 5, which gives you your trigonal bipyramidal, and then octahedral would have a total of 6 sp3d2, and here we would have 5 sp3d orbitals. Okay, so here is just a summary, again, of based on the electron cloud geometry that you have, what the hybridization of those orbitals would be for each central atom. So now we're going to do a little bit of practice. And in this practice, we're going to look at this first carbon on the left, which we've labeled as carbon A, and we're just asking, we're asking what is the hybridization of that carbon atom. Okay, and the way that we determine this is that we have to count up the total number of atoms that are attached to that carbon, as well as the total number of electron pairs that we have around that carbon. So if you need to, again, go back and review electron cloud geometries and how you determine what it is. But on that carbon A, we have a total of 1, 2, 3, 4 atoms that are directly attached to that carbon and no lone pairs. So if we have 4 outer atoms directly attached, that gives us a tetrahedral structure, and so the hybridization around that carbon must be an sp3. Okay, so we're going to erase that, and then we're going to look at the second carbon labeled. So now we're looking at carbon B here. And again, how many atoms are directly attached to that carbon. And we don't care whether the bond between it is a double, a single, or a triple. It's just how many atoms. And we've got 3 atoms with 0 lone pairs. So 3 electron clouds will give us a trigonal planar structure, and therefore the hybridization on that carbon is an sp2. Okay. So now we're going to erase, and we're going to focus on carbon C. Okay, so we're going to look right here at carbon C, and again, you've got 3 atoms directly attached, no lone pairs, and so that also is an sp2 hybridization. And then the last one, carbon D over here, we've only got 2 atoms directly attached to it, no lone pairs. And so 2 electron clouds will give us a linear structure, and so that carbon is sp hybridized. Okay, now let's practice a few with the expanded octets. Again, what is the hybridization of the central atom? So looking at antimony here on the left, it has a total of 5 atoms that are directly attached with no lone pairs. That is our trigonal bipyramidal electron geometry. And so we've got an sp3d hybridization. The next one, sulfur, has a total of 6 atoms attached to it. Okay, and 6 atoms attached with no lone pairs, that's octahedral, and so we've got sp3d2 hybridization. Now the next one, xenon, we do, remember, have to count the lone pairs. So we have 4 outer atoms that are attached to that xenon, and we also have 2 lone pairs that are directly on that xenon. So we have a total of 6 electron clouds. That's an octahedral structure. And so again, that is going to be sp3d2 hybridization. So if you notice, I'm pretty much determining the hybridization of the central atom based on the electron cloud geometry. So if you can find the electron cloud geometry, then you know what the hybridization of that central atom is. Okay, and then last example, again on that chlorine, we do not care about the lone pairs on the fluorine, just the lone pairs on the chlorine. Okay, so that's a total of 5 electron clouds around that chlorine, and that gives us an sp3d hybridization. Okay, we've got one more example we're going to do. Just keep in mind that when you're on your homework or on your test, you are expected to be able to create these Lewis structures if they're not automatically given to you. So you may be given a molecular formula and asked to draw out the Lewis structure before determining the hybridization. And in this next example, you might be given a skeletal structure where you can see the connectivity of the atoms, but yet it's not complete. Okay, so you might have to finish off that Lewis structure and then determine the number of sigma and pi bonds. So if this happens, I think it's easier to go ahead and count to figure out the number of sigma bonds. And remember that first bond that occurs between 2 atoms, regardless of whether it's single, double, or triple, that first line is going to represent a sigma bond. Okay, so if I count up the number of bonds that I see, right, every line represents a bond. So that's 5, 6, 7, 8, 9. So there are 9 bonds in this skeletal structure. And so I already know that I'm going to have 9 sigma bonds. Okay, and then the tough part is going to be figuring out how many pi bonds that I have. So I'm going to erase for a second, counting up those number of bonds. Now, to complete the Lewis structure, it will help if you first count up the total number of valence electrons. And remember, when we're doing this, all right, we are counting up the number of valence electrons that we have for each type of atom, and we're going to multiply it by the number of those atoms that we have in the structure. And so in this structure, we only see carbons and nitrogens. So remember, carbon from the periodic table, because it is in group 4A, it has 4 valence electrons. And if we count up the number of carbon atoms in this structure, we've got 2, 4, 6. 6 atoms in the structure. Okay, now nitrogen, we've got on the periodic table, nitrogen is in column 5A, or in period 5A. So that's going to be, group 5A. So that's going to be 5 valence electrons, and we have a total of 4 nitrogen atoms in this structure. So 6 times 4, we've got 24 coming from the carbon, plus 20 from the nitrogen, for a total of 44 electrons in this system. Okay, now remember that every line represents 2 electrons. So each line here, right, is 2 electrons. And we've already counted that we have 9 lines or 9 bonds shown. So we can subtract 18 electrons that are already shown in this structure. Okay, so that should give us 26 electrons left over that we're going to have to fill out in this Lewis structure. Now, it also helps to remember that based on the group number that you have, it kind of tells you the number of covalent bonds and the number of lone pairs that you typically have for that type of atom. So usually carbon likes to have 4 bonds and 0 lone pairs. Nitrogen typically likes to have 3 bonds and 1 lone pair. Now this is not perfect system, right? Oxygen, 2 bonds and 2 lone pairs. So carbon dioxide is a great example of this, where we have oxygen likes to have 2 bonds and 2 lone pairs, but that's not always the case, right? There's plenty of times that we will see an oxygen have a single bond and 3 lone pairs, and that gives it a formal charge of -1, whereas the 2 bonds and 2 lone pairs gives it a formal charge of 0. So that's why oxygen typically likes to have the 2 bonds and 2 lone pairs, because it likes to have a formal charge of 0. But if not, it does also prefer a formal charge of -1. And so we'll kind of see that both ways. But this gives you at least a starting point when you're trying to develop these Lewis structures. So knowing that carbon likes to have 4 bonds and that nitrogen likes to have 3 bonds, we can then go back and fill in nitrogen with 1 lone pair on each nitrogen. And to give nitrogen 3 bonds, if it's only attached to a carbon, then we're going to have to go in, and I'll change my color so we can see this. We're going to have to go in and add a double bond and then a triple bond to give that nitrogen 3 bonds to the carbon. Okay, so each nitrogen is going to be triple bonded to each one of those carbons. Okay, and then that automatically gives each one of those carbon 4 bonds, because we've got 3 from the triple bond here plus 1 going to the center carbons. So each carbon has a total of 4 bonds, which is what it would like to have, and no lone pairs. But the issue is, if we look at these 2 carbons in the center, right, they only have 3 bonds each. We've got 1, 2, 3 bonds to that carbon. So if we want to make sure that each carbon has 4 in the center, and we don't want to affect the carbons on the outside that already have 4, then we're going to add a double bond in that center. So notice how I'm always working from the outside in, making sure that they match the rules associated here starting out. And then I would go back and make sure that I have used up all 26 electrons in all those bonds that I added. So I'm going to go back and erase real quick, just so we can see exactly what I've added to this structure. Okay, and so all of those red marks from the lines as well as the lone pairs should add up to 26 electrons that I had left over. Okay, and so if I went through and counted, that would be 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Okay, so now I've used up all 26 remaining electrons, nothing left over. Everything is going to have a formal charge of 0 and be happy, because they are following this rule here of 4 bonds for carbon and 3 bonds for nitrogen. Okay. So this would be my final Lewis structure here. And with that, if we want to count up the number of pi bonds, right, the pi bonds are going to be any of the second or third bonds that we add if we see double or triple bonds anywhere. So for example, right, this here is a pi bond, and then we also have a pi bond on this side as well. So you've got 2 pi bonds for every triple bond. So there's 2 here, 4, 6, 8, and 9. So we should have 9 sigma bonds and 9 pi bonds in this structure. Okay, so it does take a little bit of practice, but going back and reviewing those Lewis structures, if you build the Lewis structure, then every single line represents a sigma bond, and then the first bond in a double or triple bond also represents sigma, and then any remaining, right, the second bond in a double bond is a pi bond, and then the second and third bond in a triple bond is also a pi bond. Okay. So that's probably the most complicated hybridization problem that you'll get. Now, with the valence bond theory, there are some limitations. So it is better than Lewis theory at predicting your bond strengths and your bond lengths. But the issue is that valence bond theory still doesn't do a great job with delocalization. So remember, that's talking about your resonance structures. And it still isn't perfect at predicting magnetic behavior. So again, that diamagnetic versus paramagnetic. And so we're just going to talk briefly about molecular orbital theory. So remember that molecular orbital theory, that is where we're dealing with molecular orbitals instead of hybridizing the atomic orbitals. Okay, so atomic orbitals, those are going to be a region of space in an atom, but a molecular orbital, that's going to be a region of space in a molecule. And so we use the S, P, D, and F when we're talking about atomic orbitals, but we're going to use pi and sigma symbols when we're talking about molecular orbitals. So, in physics, we learn a little bit about waves, and when they combine, they can either be constructive or destructive. Right, so when waves are in phase, when the peaks align, then we have what we call constructive interference, and so we'll end up with a greater amplitude when the waves are in phase. Now, if the waves are out of phase, we have what we call destructive interference, right? So that's when a peak matches with a trough of a wave, and so they're mismatched, out of phase, and they result in either less or no amplitude, right? So here they just completely cancel each other out, and we end up with a straight line. So wave functions, they can also combine in either a constructive or a destructive way. And what happens is we create what we call bonding and anti-bonding orbitals. So anti-bonding orbitals, those are going to be represented by an acertic next to your molecular orbital symbol. So bonding orbitals, those are going to be lower in energy, and your anti-bonding orbitals, those are typically going to be in higher energy. And when we're representing those bonding orbitals, those are going to come from constructive interference, and we're going to have sigma and pi bonding molecular orbitals. And then the anti-bonding orbitals, those come from destructive interference, and so they're going to have more energy, and those are represented again by the star or the acertic next to the symbol. So electrons in the lower energy bonding orbitals, those are going to be what hold atoms together. Electrons in the anti-bonding orbitals are going to cancel that effect out. And so if we want to determine the bond order, we're going to use this simple equation where we take the number of bonding electrons minus the number of anti-bonding electrons and divide by 2. Okay, so in this example, right, we have a hydrogen molecule, and so on either side of the diagram, you're going to see that you have your original atomic orbitals. Okay, those, as the two hydrogen atoms approach, are going to kind of disappear in the system, and we're going to recreate these molecular orbitals in the center. Okay, so we almost ignore those atomic orbitals, right? Because those electrons are going to go into the molecular orbitals here, and we form this sigma 1s bonding molecular orbital. Okay, so if I want to calculate the bond order for this system, I count up the number of electrons in the bonding orbital, which is 2, right? So that's where this 2 is coming from. And then we're going to subtract out any electrons that are in the anti-bonding orbital that is higher in energy. And so we can see we have no electrons there currently, because each hydrogen atom only carried 1 electron for a total of 2 in this system. And so 2 minus 0 will give us 2, divided by 2 gives us a bond order of 1. And that is going to be what we see with 2 hydrogen atoms. We have 1 bond, right, 1 sigma bond between those 2 hydrogen atoms. Now, this is an example of if we had 2 helium atoms. Remember, helium atoms each contain 2 electrons. And so we would have a total of 4 electrons in the system. Okay, we would have 2 electrons in the bonding orbital, and we would have 2 electrons in the anti-bonding orbital. And so if we were to calculate the bond order here, we would have 2 electrons, right, that are bonding, and we would also have 2 electrons from the anti-bonding. And so that would give us a bond order of 0, and that's what we would expect. Helium atoms, they're from the noble gas column, so they tend to like to be alone, and they're not going to form bonds between each other. Okay, so this would give us a bond order of 0, and it would be unstable because those anti-bonding electrons would cancel out the bonding electrons. Now, when we're looking at the molecular orbital diagrams, just keep in mind that the highest occupied molecular orbital, or HOMO, that is going to be the orbital that contains the highest energy that contains electrons. So in the example here, our highest occupied molecular orbital would be a sigma 1s, okay, because it's the highest energy that still has electrons in it. Now, when all the electrons are paired in our molecular orbitals, we call this diamagnetic. And remember, we don't care about the electrons that are shown in those atomic orbitals, right? Those are the original orbitals, but those disappear as we create these molecular orbitals. And so both of these electrons are paired up. We don't have any electrons that are unpaired, and so that's going to be considered diamagnetic. Now, in an example of 2 oxygen atoms that come together, here you're going to have 2 unpaired electrons in the highest molecular orbitals, right? And your highest molecular orbitals in this case would be a pi, an anti-bonding pi orbital, and it's the 2py and the 2px. Okay, those are going to be your highest occupied molecular orbitals, and you notice that you have 2 unpaired electrons here at the top, and so that's going to be what we call paramagnetic. And again, when we're trying to determine whether something is diamagnetic or paramagnetic, we're going to ignore those atomic orbitals and focus just on the molecular orbitals. And keep in mind that you would not have to be able to form this molecular orbital diagram from scratch. You would have to be able to fill it in. So we're going to do some examples of that. Okay, so in this example, we're going to look at NO negative. Okay, so a nitrogen oxygen atom coming together, and it is ionized with an extra electron. So If we want to fill out our molecular orbital diagram, the first thing that we're going to need to do is determine the total number of valence electrons. So I need to figure out, let's see, total valence electrons in NO negative. Okay, and give me just 1 second. All right, so total valence electrons in NO negative, and from nitrogen, remember periodic table, it's in group 5A, so nitrogen is going to have 5 valence electrons, plus our oxygen is going to have 6 electrons, again it's in group 6A, and then we have to add 1 extra electron because of the negative charge. Remember, electrons carry negative charges. So that's going to give us a total of 12 valence electrons in the system. Okay, so if we want to add those 12 valence electrons, we're going to add them to the molecular orbitals here in the center. Okay, so to populate the orbitals in the diagram, remember that if we only have 1 orbital in that energy level, we're going to fill it immediately with 2 electrons. Then we're going to jump up to the next level, fill that with 2 electrons, and then when we get to a level that has 2 orbitals with the same energy, remember we have to fill up 1 electron at a time in each orbital before we can go back and fill that orbital with the second electron. Okay, so I've got to use up 12 total, and right now I've used up 2, 4, 6, 8. 2 more would make 10, and the last 2 will go in that sigma anti-bonding orbital. Okay, so for a total of 12 electrons, the first question that it asks is this diamagnetic or paramagnetic? And all of the electrons are paired in your molecular orbitals. Okay, there's nothing unpaired, and so that's going to be considered diamagnetic. What is the bond order? So again, to do the bond order, we have to find all of the bonding electrons. So those are going to be the molecular orbitals that do not have a star associated with them or an acertic symbol. Okay, so we've got 1 sigma bonding orbital here at the bottom, 2 pi bonding orbitals, and a second sigma bonding orbital up top, for a total of 8 bonding electrons. Remember, there are 2 electrons for each orbital. And then subtract out the anti-bonding electrons. Okay, so we've got, and here I'll change the color, we've got 2, 4 anti-bonding electrons, so minus 4. And then divided by 2. So 4 divided by 2 will give us a bond order of 2. And then identify the highest occupied molecular orbital. That is going to be up here, this anti-bonding sigma. Okay, now let's try one more example. So this time we're looking at carbon monoxide. Okay, and we'll just assume that we've got carbon here on the left and oxygen here on the right. And in the center represents our molecule, and I'll put it up top, of carbon monoxide. Okay, so again, we first have to determine the total valence electrons. And carbon is in group 4A, so it's going to have 4 valence electrons. Oxygen has 6, it's in group 6A, for a total of 10 valence electrons. And then again, starting from the bottom, we're going to fill it up with 2, and then keep going, 4, 6, 8, 10. Okay, and if you wanted to see where they originally started out, carbon would have 4, so it would have had 2 in the 2s and 2 in the 2p orbitals. Oxygen would have had 2 in the 2s and, let's see, 1, 2, 3, 4 in the 2p orbitals. Okay, remember that on the left and on the right, these are your atomic orbitals. And then in the center are your molecular orbitals, which is what we're typically focused on. So, is carbon monoxide diamagnetic or paramagnetic? Again, in the center, that's what we care about, and all of the electrons in the center are paired up, and so we have diamagnetic. And then what is the bond order? So our bonding electrons are going to be the ones where we do not have the star. Remember, your anti-bonding orbitals are going to be higher in energy. So we have a total of 2, 4, 6, 8 bonding electrons, and we only have 2, and again, I'll circle it in a different color, 2 anti-bonding electrons. Okay, and we're always dividing by 2. So 8 minus 2 is 6, divided by 2 gives us a total bond order of 3. And that makes sense if we were to look at a carbon monoxide molecule. It's going to have a triple bond between that carbon and oxygen, which gives it a bond order of 3. And then the highest occupied molecular orbital, that's going to be here. That's that sigma 2p orbital. Okay, so that ends our lecture on valence bond theory and molecular orbital theory.